page you see in front of you right now looks an awful lot like a page you saw a couple of weeks ago in Physics 20. The title of that other page said velocity, sorry, the title of this one says velocity time graphs. The title of the other one said position time graphs. But the general shape of those graphs were the same. We went through the shape of those position time graphs and identified what each of them represented. Okay, what situation each of them described. I want to do the same thing right now with the velocity time graphs of those same shapes. If this first graph that you see was a position time graph with a straight line, it would represent constant velocity. It does not represent constant velocity when it's a velocity time graph. You can clearly see that the velocity is increasing. That's not constant velocity. What do you think it represents this time? Yep. Good. Constant acceleration, uniform acceleration. So it's not enough to say acceleration. It is enough to say constant acceleration or uniform acceleration, meaning that it's speeding up, it's getting faster and faster, but the rate at which it's getting faster and faster remains the same. What's the second one mean? If this was a position time graph, then we would say this was constant position. In other words, it's stopped, right? It's not moving if it's a position time graph. But it's not position time graph, it's a velocity time graph. And you can see that clearly it's not stopped because the velocity is, I don't know what it is, but it's not zero. What does it mean? Good. This one means constant velocity. The velocity is not changing. You could say constant velocity, you could say uniform velocity, whatever you want there. But just like it's not okay to just say acceleration in the first one, it's not okay to just say velocity in this one. It's got to be constant, uniform, something like that. Third one, if this was position versus time, it would mean constant velocity, but in the negative direction. Not constant decreasing velocity. That doesn't make any sense. It can't be constant and decreasing at the same time. Constant negative velocity. Constant velocity, but going in a negative direction. Okay, but this isn't position time. This is velocity time. So what does it mean? Good. It's a uniform negative acceleration. Or what's another way to say uniform negative acceleration? Uniform deceleration. Mackenzie, if you said uniform negative acceleration on a quiz or a test, I would absolutely take that. It means exactly the same thing, right? I'm going to just write the term deceleration because that tends to mean more to people. People tend to understand that term a little bit better. They understand that that means slowing down. Right? The velocity is decreasing, but it's decreasing at a constant rate. What about this one? Position time graph, this would be acceleration, speeding up. Well, yeah, it is. It's still acceleration. But this time it's not a constant acceleration by any means. It's an increasing acceleration. So not only is it speeding up, listen carefully to what I'm about to say because it's kind of a mouthful here. It's not only speeding up, the rate at which the velocity increases, and the velocity is increasing, right? The rate at which the velocity increases. So it's speeding up, and it's speeding up quicker and quicker and quicker all the time. It's kind of like you're driving your car, you're sitting at a stop sign in your car, you put your foot on the gas pedal just a little bit, and you speed up, right? And if you keep your foot on the gas pedal a little bit, you keep speeding up for a while. But if you keep putting your foot further and further and further and further down, not only do you keep speeding up, but the rate at which you speed up keeps getting bigger. You keep speeding up quicker and quicker. Does that make sense? Put your foot on the gas a little bit, you speed up at, 5 meters per second squared, let's say. Put it down further, and it's 10 meters per second squared. So not only is your velocity increasing, the rate at which your velocity is increasing increases. So we're going to say that this is an increasing acceleration versus a uniform acceleration or constant value. And finally, the last one. Velocity time, if it was position time, it would be slowing down, right? Velocity time, it isn't slowing down. Hey, it's still speeding up. Right? Velocity keeps getting bigger and bigger in this graph. The velocity keeps getting bigger, but it's getting bigger slower. So what we're going to say here is that this is a decreasing acceleration. It's still accelerating. It's still speeding up. Don't think that it's slowing down. It isn't. The velocity keeps getting bigger and bigger and bigger. It's accelerating, but the rate at which it's accelerating decreases. So to put it in a different way, the rate at which the velocity increases, fill in the blank. The rate at which the velocity increases, what's the word? Decreases. So the velocity is still increasing, but the rate is decreasing. Good. All right, we can find a number of things from these velocity time graphs, the same as they could from position time graphs. So we're going to go through 4 things here, and then we'll do an example that's on the front side of your worksheet that you got a minute ago. Finding the instantaneous velocity on a velocity time graph. Take a stab at that one. Anyone? Yep, Cody? Up and over, right? If you want to find something that appears on the y-axis, it's going to be up and over. It's like finding the position on a position time graph, finding the force on a force versus time graph, finding the final velocity on a final velocity versus initial velocity graph. Anything that appears on the y-axis, you want to find that, it's up and over. Change in velocity on a velocity time graph. Yep. VF minus VI. Remember, with position time graphs, one kind of went into the next, right? You got position, then you got displacement, the change in position. Same kind of deal here. We got velocity, then we got change in velocity. So get one velocity, get another, and then subtract them. Acceleration. One goes into another again. Yeah. Good. So you got a velocity, and then you get another one and get the change. And then you divide the change by the time to get the acceleration. This is the tough one. This is the one that doesn't really go with the rest. Doesn't really go with any of the things that we've learned yet in Physics 20 with position time or velocity time graphs. The displacement on a velocity time graph, I'm just going to tell you this one. Okay, unless you know it. Your hand was starting to go up there. No, be careful with that, because if you use velocity times velocity times time, you're assuming that velocity is uniform, and it isn't, right? Okay, that's a group B problem, really, because it's accelerating. Yeah? Yeah, good. It's the area. It's the area between the line and the x-axis. So, this area right here. But you could see a situation, I suppose, where you had a graph that looked like this. We had a line that was partly above and partly below the x-axis. In that case, you'd find this area, and then add them up. What would be special about that addition, though? What would be special about it? This is positive, and this would be negative because it's below the x-axis. Right? We're going to do that example that you see on the front of your worksheet now, okay? We'll keep in mind that natural transition from one thing to the next, right? Velocity, then change in velocity, then acceleration. Well, and then the last thing, we just have to remember that that's going to be the area. So let's take a look at the front of that sheet now, please. What's the velocity of the object at 4 seconds? What are we going to do for that? Cody, I know that you know what we're going to do for that. Up and over. So at 4 seconds, we're going to go up. We're going to go over. The velocity at 4 seconds is 15 meters per second. Just like if I wanted to find the position at 4 seconds on a position time graph. The change in velocity over the entire graph. Well, the final velocity looks to be 33. The initial velocity looks to be 3. The change in velocity is final minus initial. 33 minus 3 is 30 meters per second. What about the acceleration of the object over the entire graph? Well, from one to the next, right? Position. You know how to get a position? Displacement is easy. You know how to get a, you know how to get a velocity? Change in velocity is easy. You know how to get change in velocity? Then we can get the acceleration pretty easily. It's delta V over delta T. It's 30 meters per second over 10 seconds. It's 3.0 meters per second squared. And finally, the displacement. It's so close to a triangle, but not quite. We got to break it up a little bit here. Here's a triangle. The area of the triangle is 1/2 base times height. The base is 10. The height goes from 3 to 33. The height is 30. But then there's a rectangle down below that we also have to include. This is going to be base times height, or length times width. 10 times 3. The height is 3. Both of them are positive, right? Because they're both above the x-axis. Add them up and you get 180. Your homework is questions 1, 2, 3, and 4 on the back of that worksheet. See what you can do with those. Guys, listen, that should take you, this is a 10 maybe 15-minute homework assignment. Okay, if it's taking you half an hour, what should you do? Come see me. Yeah, it's taking you too much more than 10, 15 minutes. Yeah, absolutely. You work on it now. If you finish it before the end of class, great. If not, then finish up for homework tonight, and we'll take a look at it tomorrow.